Hello class. Today what we are going to talk about is proving triangles similar specifically by angle-angle. Alright. Now before when we were talking about congruent triangles, one of the things we did look at was, hey, what if all three of the angles are congruent, right? Does that give us congruent triangles? And we saw, no, it does not. However, having the angles congruent does give us similar triangles. And we also know by the third angles theorem that if two of the angles are congruent, then that third angle is also congruent, which means we really don't even need all three angles to be congruent, right? All we actually need are two. As long as we have two angles of one triangle congruent to two angles of a second triangle, then the two triangles will be similar. They will not necessarily be congruent, but they will be similar. All right. And so then if you know one side, you can use proportions or scale factor, whichever one you like, to find the other sides or area, perimeter, whatever it is you want to do. All right. So the important thing is, in order for triangles to be similar, all we need to prove is that they have two angles congruent. All right. And what this is really good for is indirect measurement. And this is something that you may have seen before, but it's something that's actually useful. And I've used this outside of school. I've had students come back and say, hey, Mr. Barnett, we actually used that stuff you taught us last week. And this is one of those things. All right. Indirect measurement, what this does is this is a way to measure things that are very difficult to measure directly. Before we do indirect measurement, right? These are things like flagpoles, or how tall is this tree, or how wide is the river, things like that. And so we can't measure it directly because it's very difficult to climb a flagpole and drop a tape measure down, unless you have like a cherry picker or something to lift you up there. And measuring a tree, also difficult to measure straight up and down because all the branches get in the way, that kind of thing. So we use indirect measurement, and we do this using similar triangles, okay? And one of the ways to do this, and one of the most well-known ways to do this, and you've probably seen this in textbooks all the way back through junior high, maybe even into elementary school, is to use shadows. I can't climb up and measure that flagpole, but I can measure the shadow along the ground, right? And so I can measure my shadow. I can get my friend to stand still, measure how tall he is in his shadow. And the thing is, since the sun is coming in at the same angle, right, for both people, because the sun's in the same spot, so it's coming at the same angle, that means that this angle here is congruent to this angle there. And assuming, of course, that the flagpole was put up properly and your friend's not leaning over, they're both going to be perpendicular to the ground. And so I have a right angle, and I have this other angle right there. So I have two congruent angles. And so we have angle-angle similarity. So we can set up a proportion, and we can cross multiply and divide, use cross products, and find out that the flagpole is 20 feet tall. All right. This is one method of using indirect measurement. There are several of them, lots and lots of them. This is just one. But all of them, pretty much, that I can think of, all of them use similar triangles or trigonometry, but we're not dealing with that. Those are a bit more annoying. Yeah, they all are going to use, for today, similar triangles. So let's take a look, see what we got. Do some examples. Let's see here. All right, in exercise 1 and 2, we want to determine, are these triangles similar? If they are, we want to write a similarity statement, and then we have to explain our reasoning one way or the other. Okay, so triangle 1, number 2, we have triangle ABC and triangle DEF. Are they similar? Well, we do have to have two angles congruent, right? Really, we need to have three, but two will prove it. So, let's see here. I've got a right angle for both of them, so that's one angle, and now I've got 15 degrees and 75 degrees. Those aren't the same, but they also don't correspond to each other, so that's okay, as long as this one is 75 and that one is 15, right? So we're just going to find one of them. It doesn't matter which one we have. Let's see. This is a right triangle. And I know that the angles of a triangle add up to 180. It's a right triangle, which means the acute angles are going to be complementary. So I can just come over here and I'm going to find ABC, find the measure of angle C. So I can just do 90 minus 15. Let's see, that would be 5, and that is 75. So the measure of angle C is 75 degrees, right? And now, hey, I have two angles congruent to those two angles, and so I have angle-angle similarity. Angle-angle similarity. It is important that you specify this as angle-angle similarity, not angle-angle something else. All right. So they are similar, so I need to write a similarity statement, which, remember, this looks just like a congruent statement. It just has a similar sign instead of a congruent sign. So ABC, we'll call this triangle ABC, and we use this little squiggle there for similar to triangle. Now this one does matter. It has to have the same order as the first triangle. So angle A corresponds with angle E, because they're both right angles. So E. Angle B corresponds, see, B is the 15-degree angle, and so this one is going to be the 15-degree angle. F, E, F, and C is our 75-degree angle. It's going to go with D. So triangle ABC is similar, not congruent, but similar to triangle EFD. All right? All right, I would like for you to pause the video and work out number 2. Alrighty, you're back. Let's see how you did. So first things first, we find, are these similar? We need to get two angles that are congruent to each other. Well, we already have one. We have these 30-degree angles. Those are congruent. And so now we need to check the other ones. Well, I've got 116 here. I've got 44 there. And looks like it might work. Let's find out. We'll use ABC. Why not? We need to find that third angle. So all three angles of a triangle add up to 180 degrees. And I didn't know what that is, so real quickly, this is 116 and 30, which is 146. So I'm going to take that 146 and subtract it from the 180. And that's 4, so that's a 7, and I have 34 degrees right here. 34 degrees. I needed 44, didn't I? Those doesn't work. So I do not have congruent angles. So I'm going to write here that, let's see, my paper is wiggling. Angles are not congruent. And I'm in another room. Try this again. Angles are not congruent, so the triangles are not similar. Triangles are not similar. No. All right. Gotta have two angles congruent, and I've only got one. Because it doesn't matter what that is, it's not going to match up with those. Okay, let's take a look at 3 and 4. In exercise 3 and 4, we want to show that the two triangles are similar. So it's telling us, hey, these are similar. Prove it. Prove it. Okay, so number 3, we have triangle ACE, the big triangle, and then we have triangle BCD, this little one inside of it. Okay, so we need to show that they're similar, which means we need to have two angles congruent. Okay, so first, angle C is in both triangles, isn't it? So we know that angle C is congruent to angle C by the reflexive property. But now we need another one. Well, if you'll notice, these two lines here, these two sides are parallel to each other. And if those are parallel, then that means that here angle AEB and angle BDC are corresponding angles, right? And if the lines are parallel, the corresponding angles will be congruent. So that means that angle C is congruent to angle BDC by the corresponding angles theorem. Corresponding angles theorem. Right. And now I have two angles that are congruent to each other, two angles in the big triangle congruent to two angles in the little triangle, and so my triangles will be similar by angle-angle similarity. Angle-angle similarity. All right. Now, of course, I really didn't even need to say the reflexive stuff, did I? If I've got corresponding congruent angles here, these angles here also could have used corresponding angles theorem for angle EAD or EAC and DBC. Would also been corresponding angles. All right, so pause the video real quick, see if you can come up with number 4. All right, let's see how you did. We just need to get two angles congruent, right? Well, looking at this, I've got parallel lines, don't we? Parallel lines, which means we can do very similar to what we had here. We can say that this angle is congruent to this angle because those are alternate interior angles, right? And not only that, these two lines are parallel, which means I've got alternate interior angles right here as well. And so I know that angle PSQ is congruent to angle, what would that be, RQS, and angle QSR is congruent to angle, which one am I looking at? This one here, SQP, which means I have two sets of congruent angles, and okay, well, first off, I gotta say why. We know this by alternate interior angles. Alternate interior angles. And so we have angle-angle similarity. All right. Now, if you did it differently, there's another way we could have done this. Since you know that both sets of opposite sides are parallel, this is a parallelogram, which means we have parallelogram opposite angles theorem says that angle P will be congruent to angle R. So you'd use that to get one of your angles, then alternate interior angles to get one of the other ones. Right? So a couple of different ways you could have done that one. All right, let's take a look at this with some numbers. All right, let's see, get this whole thing on there. There it is. All right. Now, okay. So we have this diagram, and we're going to use this for the rest of these. The measure of angle, we need to find all of these answers. So we need the measure of angle AGB. Where is measure AGB? AGB is right here. Okay. Well, AGB. This is a right triangle, right? This little top part. And that has to add up to 180, but it's a right triangle, which means the acute angles have to add up to 90. So we are going to have, I'm just going to do it here because I'm probably going to use all this space. 90 minus 63, right? Minus this angle here. And that gives me, let's see, that makes that an 8, that's 10, so I have 7, and so this is going to be 27 degrees. All right? Now we need the measure of angle EGD. Let's see, EGD. Well, these two, if you'll notice, those are vertical angles. They're congruent to each other. So this is also going to be 27 degrees. Which means, by the way, I have a right angle. I have vertical angles. These two triangles are going to be similar. Angle-angle similarity. Now I need the measure of angle BCG. And that one's going to be a little bit more problematic. All right, let's see here. I know this is 63 degrees for this triangle, but I don't know what this entire angle is here. Hopefully these triangles are congruent, in which case I can figure that out. So I'm going to skip that and come back to it in a minute. All right, I need the length of segment AG, which would be A 2G. Well, let's see here. I have one side. It is a right triangle, so I could do Pythagorean theorem, but I would need to know that other side, whatnot. And I don't know that other side. So we'll come back to that one too. The length of AB. Hey, there we go. We're going to find that side. And that's, well, if this triangle is similar, here's a question. Are these two triangles similar? This whole one here and this little one here, are those two triangles similar? Yes, they are. I know this is 63 degrees, right? I know this triangle is similar to it because I've got vertical angles, I've got a right angle, so that means I've got angle-angle similarity, or I could just say third angle congruence, right? So I know this one's going to be 63 degrees. And the bell's going to ring and interrupt me, always nice. Anyways, so I know this triangle, this angle is 63. I have vertical angles here, AGC and FGD, so that gives me two angles, so I have angle-angle similarity. So I know the little, well, this triangle here, this half of the hourglass-looking thing, and this half are going to be similar. So I can use similar scale factor, or I could use proportions. Either way, doesn't matter. I'm going to use scale factor because y'all have done proportions forever, so something slightly different. Okay, so scale factor, I know that the altitude is 3 for the little one and 6 for the big one. So if I'm going from little to big, so if I'm going this way, my scale factor is going to be 6, the new one, over 3, which is 2. So if I'm going to go from little to big, I'm going to multiply by 2. Well, FD here has a length of 3. And if I know what AC is, then I can find the length of AB, because I know that part's 3. So I'm going to take FD times 2 to equal AC. So that's 3 times 2 equals 6. So I know that this entire thing from A down to C is 6, right? And if A to C is 6 and B to C is 3, that leaves me 3 left over for AB. So that's going to be 3. I'm going to write it down so I don't forget it. Okay. Now, I needed that a minute ago to find AG, didn't I? So now that I have it, let's do AG. I have a right triangle, so I can do Pythagorean theorem, right? So that would be the square root of 3 squared plus 6 squared. Well, 3 squared is 9, and 6 squared is 36, so 9 plus 36 would be 45. I don't want to leave square root of 45. That's not proper, right? We've got to simplify it if we can. So remember, we simplify square roots like this. Square root of 45 would be divisible by 9 and 5. So 45, we'd have the square root of 9 and the square root of 5. Are either of those perfect squares? Yes, 9 is a perfect square. And so this becomes 3. Square root of 9 is 3. That is out from the radical, so it's done. And here we have square root of 5. 5 is prime, so that's done. And I have 3 times the square root of 5. So that's what I'm going to put right here. 3 square roots of 5. All right. Now we need to find the length of FE. All right, so FE is this piece right here, so that's going to correspond with that piece there. Well, now I'm going from big to little, so I'm not going to multiply by 2. Now I'm going to divide by 2. Or take it the other way around. My scale factor going this way would be 3 over 6, which is 1/2. So we'll either divide by 2 or multiply by 1/2, whichever way you like it. And so this is going to be 3 times 1/2, and half of 3 is, of course, 1.5, or 3/2, whichever way you like. Okay, so now we need the length of ED. So we have FE, we need ED. I could do it this way again, 3 times 1/2, right? Or, hey, the whole thing is 3, so I could just say 3 minus 1.5, which is, of course, another 1.5. 1.5. All right. Which means, if you'll notice, that means this is going to the midpoint, right? It is also the altitude. And if you recall, if the altitude and the median are the same line, we have an isosceles triangle, which means the base angles are going to be congruent. So the measure of angle BCG is going to be the same as BAG, which is 63 degrees. All right. Okay. Next one we need the length of GF. Well, GF is right here. That would correspond with CG, right? But it's isosceles, so it's also going to be the same as AG. These are similar figures, so we're going to use our scale factor to take AG down over here. So what we have is 3 square roots of 5 times 1/2. Remember, we just multiply straight across with fractions, so this becomes 3 square roots of 5 divided by 2. And we're going to leave it like that. Okay, next one. Number 13. We want triangle AGC is similar to, well, it's going to be similar to a triangle because it can't be similar to some other shape. Right? Similarity, same shape, different size. So we have AGC, so that is this big half of the triangle there, or the shape there, and that is going to go with the other side. Well, as we saw, A corresponds to D, right? Because this triangle was similar to that one. So A goes to D, so we have D. G right here, well, that's a vertical angle with a G over there, so DG. And then our last one, point C, is going to correspond over here across the way to point F. So DGF. You got to make sure you have these in the right order, otherwise things get all messed up. Remember, A goes with D, G goes with G, C goes with F. They have to correspond to each other. All right, so there's that. We have one last problem, and this is going to be another indirect measurement thing. All right. What we have here, your friend is 6 feet tall. She places a mirror on the ground 16 feet from the base of a tree and stands 8 feet from the mirror so that the top of the tree is reflected in the mirror, as you see here. So she's looking down at the mirror. She sees the tree reflected in the mirror, right? First, we want to explain how this can be used to find the height of the tree, and then we're going to actually do it. All right. Well, here's the thing. Assuming, of course, that our friend and the tree were looking at height. Remember, height is always a perpendicular distance. So that means these are going to be perpendicular, right? And then from there, we have this triangle, right? We have a triangle here, we have a triangle there. And if you'll remember from a physics class or a science class, sometime you've had some science class that talked about light bounces off of things, reflects at the same angle that it hits the surface. Right? So that means whatever angle this hits the surface is going to be congruent to this angle here. All right? So now we have the right angle, and we have these two angles that are going to be congruent to each other. All right? So we need to write this down. And so, since height is always perpendicular, since height, because it does say to explain, is perpendicular, and light reflects at the same angle it hits the surface. I don't know what that's actually called. Whatever. Since light, yeah, whatever, reflects off a surface, yeah, I'm not a science guy, so I don't really know what it's called when it comes in like that, at the same angle it hits, hits the surface, so hits it, let's say that, we have angle-angle similarity. There is angle-angle similarity. And so now we can use either scale factor, or we can set it up as a proportion. And since the one on the front of this was a proportion, I'm going to use scale factor again just because this will actually have a nice scale factor. So I'm going from my friend's triangle here to that triangle. So it's going to be new over old. So that's 16 over 8, which is 2. That's going to be my scale factor. And then I can just take 6, the height of my friend, times my scale factor, 2, which gives me 12. So the tree is 12 feet tall. And this is pretty useful. I have used this more than once. I honestly use this a lot more than I would use the shadow method that was up here at the front. Just because if I'm going to measure something tall, odds are that shadow is longer than my tape measure. But I can take my mirror and I can just move it closer and move me back or something like that to where it gets within range and I can actually measure. So I find this one a lot more useful. Anyways, there it is. We have angle-angle similarity and indirect measurement. Remember, to do indirect measurement and to show two triangles are similar, all you need to do is show that you have two angles congruent between those two triangles. Right? And then you can measure stuff that you can actually reach, like the ground and the height of your friend. You know, again, just got to measure on the ground and measure the height of your buddy. And then you can find indirect measurement. And all it takes is similar figures, similar triangles. And there it is. Hopefully you found that useful, and I will see you next time.